Hi, this is Dr. Vev, and we shall be talking today about a reaction time problem involving one-dimensional kinematics. It's a situation that's pretty familiar to many of you who drive at night. So what I have here is car A and car B traveling in the same direction with speeds v sub A and v sub B. Let's assume that the stopping acceleration, sometimes called deceleration, of this car is a sub A. So the deceleration, because it's slowing down, it's negative. What I mean by this is the quantity a sub A itself is positive, but because of the negative sign, the whole thing becomes negative. So those are the decelerations of these two cars. Depending on their brakes, one of them may be better than the other, or they may be the same if they are both the same car, for example. This deer is seen. This person immediately applies the brakes to avoid hitting it. Now the question I want to ask is, what about this car? Will this car hit this car, the other car, or not? In other words, will A hit B? That's the concern here. So we're talking about a potential accident. Let's say the distance d between these cars is d at the moment that B applies the brakes. Now this problem is actually a reaction time problem because it takes a certain time for car A to even react to what B is doing. So let's call the reaction time delta t. Now if I were precise, I would make a reaction time for car A and a reaction time for car B, but we're not too concerned about car B. The reaction time here involves hitting the deer, which hopefully doesn't happen. Now, whatever time that reaction time that's taken, we're talking about what happens after he puts the brakes. After he puts the brake, this person now has to react to this person putting the brakes. So he's not directly seeing the deer. All right, to analyze this problem, it is best to consider one of the cars and then apply the same logic to the other car. Let's consider car B. Let's find out the time taken for car B to stop. That time is given by using the first kinematical equation. The final velocity of B equals the initial velocity of B plus the acceleration, which is negative AB, times the time. And we're going to set that equal to 0 because car B stops. So this gives us, solving for time, VB over AB. Next we solve for the distance that car B takes to stop. Well, that's got by the second kinematical equation. dB equals the initial velocity times the time minus 1/2 AB. It's actually plus 1/2 AT squared, but A is negative AB. So I get negative 1/2 AB TB squared. Now I'm going to substitute for TB from this equation into here. So I'll get VB squared over AB. And that's going to be 1/2 AB times VB squared over AB squared. One of these AB's cancels out. Now look at what I have. I have VB squared over AB minus half of the same thing. So the final answer is just VB squared over 2AB. Now by the way, I could have got this, if all I wanted was distance and not the time, I could have gotten this more directly using the third kinematical equation. The third kinematical equation says that the final velocity of B squared is equal to the initial velocity plus 2a times the distance. Well, acceleration is negative, so I'm going to get negative 2ab times the distance dB. And that's, since the final velocity is 0, that's going to be 0 squared. So this immediately gives me dB equals VB squared upon 2ab without the need for finding the time first. So this is a confirmation of our work so far. Whatever applies to car B applies to car A. So when car A puts on the brakes, the time taken for car A is going to be TA equals, I'll just change the subscript from B to A on that expression. So I'm going to get TA equals VA upon AA. Now what about the distance? Here you've got to be careful. The distance, you may think it's just this, VA squared, changing B into A, I get that. But you have to take into account the reaction time. For a time delta t, car A does nothing. That's captured by simply adding that extra distance, VA times delta t. So for a time delta t, he or she continues at the full speed, initial speed VA. This is sometimes called the reaction distance. So what are we after now? We want to make sure that there's no collision between car A and car B. So we want to avoid the inevitable near collision. The condition for that to be avoided is that the distance traveled by A, including the reaction distance, must be greater than or equal to the initial distance separating them, which is D, plus whatever additional distance car B has put in the meantime. That captures everything about this problem. So to avoid this inequality, I'll consider just the critical case when the equality is satisfied. So the critical case for dA, I'm going to substitute from here. So I get VA squared upon 2A sub A plus VA times delta t is equal to D plus dB, which is this, VB squared upon 2AB. I'm going to solve for D, the distance between the cars initially. So I'm going to get, I'll take this to the other side. So I'm going to get 1/2 VA squared upon AA minus VB squared upon AB plus VA times delta t. So this is a very important equation, and I have no doubt that insurance companies, for example, know about this because they are they constantly have to assess if the clients who are seeking an insurance settlement have made a mistake or not, and especially if a court case is involved. This is a very important expression because it tells us many things. For example, it tells us that if both the cars are identical in every way, they have the same, they're both traveling at the same speed, and they both have the same stopping acceleration magnitudes, then this quantity is going to be 0. And so the entire distance between the two cars only needs to be the reaction distance. Now that's like the best case scenario. What's the worst case scenario? The worst case scenario is one in which B is really good. So A sub B is very big, so it stops very quickly. If A sub B is big, then VB squared over A sub B is a very small quantity. If A sub A is really small, if the brakes are really bad on A, then this is going to be a large positive quantity. A large positive quantity minus a small positive quantity is still going to give us a large positive quantity. So if your brakes are bad and their brakes are good, that's going to be the case where you need to put the maximum distance between the two cars. Well, all these are pretty obvious statements. Let's consider another interesting case. What if your brakes are super good and B is driving a rust bucket? Well, if A sub B is really small, then this quantity is going to be a large negative number. Large negative number, that's a small positive number. So this is actually going to be a negative. The distance between the cars cannot be negative. It can it can't be less than 0. So in the ideal case, there is actually an even better case, the one where B has no brakes, but A has got super good brakes. There, you can actually be bumper to bumper and still avoid a collision because B will have scooted ahead of you after you've braked, since B's brakes are not good. So we're not considering that absurd situation. We'll just take the case of this being 0 or positive. Let's try to find the best case scenario here. The best case scenario is one where this is 0. So VA and VB, let's say that both cars are going at typical highway speeds, 60 miles an hour, although at night you shouldn't be going that fast. 60 miles an hour turns out to be 88 feet per second, an extremely useful value here. And let's suppose that the cars have the same degree of braking. So this quantity is just 0. Well, what about the reaction time? For a young adult, it's actually around 0.25 seconds. We're talking about reaction time involved in things like catching something that's dropped. So about quarter second. Okay, but at night and averaging over all ages of people, I think 0.5 seconds is not a bad estimate. In slightly old people, it can even be as large as 1 second. So let's try to find the distance d, remembering that this part is 0. So this distance d is VA times delta t. So that's going to be 88 feet per second times half a second. Seconds cancel out, and I end up getting 44 feet. 44 feet is about 3 car lengths. Now, as you all know, 3 car lengths is actually very little space between cars. I believe it's called tailgating if you do that. But in the ideal situation, 3 car lengths are sufficient to avoid a collision.